Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the thioglycosides. How thioglycoside can act as can act as a donor, glycosyl donor as well as glycosyl acceptor. With the help of suitable example, we have discussed that concept, that is a thioglycosides. So now means today what we are going to learn the next point. So because we are discussing about the synthesis of glycosides, so glycosylation method, use of phosphite. Phosphite is another term similar to as a thioglycoside. How thioglycoside can be used as a donor in the synthesis of many glycosides. Say on the same basis, there are some research papers, research papers showing that the great synthesis of that glycosides starting from the phosphate. First of all, we are going to discuss how the glycosyl phosphates are synthesized, and after that how that glycosyl phosphate can be used as a donor or the acceptor for the synthesis of number of derivatives of that. So let's see some introduction related to that glycosylation method, use of the phosphate. Specifically, we are going to we are going to see the application of phosphite. In the chemical synthesis of oligosaccharides, the overall procedure can be divided into 5 steps. Number 1, design and preparation of the building blocks, that is a glycosyl donors and acceptor with selected protecting groups. That is a step number 1. Now step number 2, manipulation of the protecting group to free the desired hydroxyl group, and this is a very prominent step as far as this phosphate glycoside is concerned. Manipulation of the protecting group to free the desired hydroxyl group so that we can form the glycosylic linkage or the glycosylic bond formation, and we will get as a different type of the glycosides starting from the different starting materials. And number 3, separation of product after each step. Whenever we are preparing, there are the number of products are formed, and out of that we have to use a technique. From that we can easily separate. Suppose the product, one product is a solid, another product is a liquid. How do we separate it? The technique used for it is a simple filtration. Filtration is a process. From that we can easily separate solid from liquids. So these are kind of the simplest technique we can use here, and we will separate it. So that is this. Now fourth one is a stereo control glycosylation. Stereo control, it is a very prominent step or the important step in every carbohydrate chemistry. That is a stereo control, regioselective, chemoselective, or what we can call it as a stereoselective. So that type of the thing you have to keep in mind, and then there is a glycosylation process. Then last one is a deproduct. After getting as a desired product, we must deprotect and product purification. After getting as a desired product, need the purification. The purity is matters a lot in getting the pure compound, and therefore whatever compound we are synthesizing here, especially as a phosphate, that should be a pure in form. Then and then we can use for the further further process or for further synthesis. And of these steps 1 to 3 are the most time consuming. Consideration efforts have thus been made to facilitate the synthesis process of, for example, many methods have been developed to reduce the number of steps in the synthesis of building blocks. Recently developed orthogonal protection deprotection strategies. There are the different strategies generally the scientists are using. Protection and deprotection strategies provide the efficiency and flexibility for the preparation of highly diversified carbohydrate libraries. To minimize protecting group manipulation, the armed disarmed strategy, the orthogonal glycosylation strategy, and the one-pot multi-glycosylation strategy have been developed in terms of simplifying the purification procedure, solid phase synthesis, and one-pot solution phase synthesis have shown great promise. Glycosylation is the controlled reaction. Glycosylation is a central reaction of carbohydrate chemistry. Because low yield, low regioselectivity and low stereoselectivity are frequently encountered, it is this step which requires special attention. Though chemists might be able to synthesize any oligosaccharide, there is no universally employed glycosylation, and therefore development of new and efficient method of glycosylation is still quite challenging. The use of glycosyl phosphite as a glycosyl donor was initiated in 1992. The Wang group and the Smith group independently reported that trimethylsilyl triflate TMSOTF could activate glycosyl phosphate in glycosylation reaction. An advantage of this method is that it provides a very high yield and alpha selectivity in the synthesis of sialic acid derivatives, and this method has been further developed by these two groups and others. Different promoters have been investigated and some unusual stereoselectivities have been reported. The purpose of this chapter is to review recent development in phosphate glycosylation and its application, and therefore we are going to discuss the preparation of glycosyl phosphates. Preparation of glycosyl phosphate. Preparation of glycosyl phosphites. Let's see how do we prepare this. Glycosyl phosphate are prepared from their corresponding anomeric hydroxyl compounds either by treatment with dialkyl N-diethyl phosphoramide DDP and 1,2,4-triazole or with dialkyl phosphorochlorodiets in the presence of Unix base, and most phosphorylation reagents are commercially available, and both methods give glycosyl phosphites in high. Example of glycosyl phosphate that can be prepared by these methods are dibenzyl phosphites, diethyl phosphites, and dimethyl phosphite. Bicyclic glycosyl phosphites such as 4 and 5 can also be prepared in the synthesis of an N-acetyl actosamine NAC derivatives. It has been shown that 4 gives better yield than the corresponding trichloroacetamates when the sugar moiety is highly electron donating, such as the 2,6-deoxy derivatives. Its diethyl phosphate derivative could not be prepared, and therefore let us see here how they can form as a phosphite. Let us try to draw here the compound, this one here OH, here COOMe ethyl groups are there, and now at this position there acetyl group, here also as a we can write here NHAC, and here we can draw this one OAC, then here we can write AOC, then backside acetyl groups is there AAC, and if you observe this structure carefully, what do you see over here? This type of the bond clearly indicate that we do not know where the hydroxyl group is present. Is it present on axial position or is it present at equatorial position? Is not mentioning, and for that purpose this type of the staggered bonds are shown over here. And this compound, this is the starting material, you can call it as a structure number 4, that is a glycoside, and this glycoside when treated with the reagent like diethyl here POBN twice in presence of 1,2,4-triazole, the resulting compound obtained will be this one, so that we will get the compound here. So the group which is obtained at axial position, then here P O BN, then O BN, and this the bond which is present at equatorial position, that is the ester group which is lying at equatorial position, and this the percentage of this product OAC, then OAC here O not here, we can draw this one here OAC, on the above one OAC we can show, and there will be a OAC acetyl group, and this is nothing but this is a glycoside from where we got as a glycosyl phosphide. This we got as a glycosyl phosphide, right? And the percentage of this is near about as a 70%, and this structure number we can call it as this is a structure number second. Now the same starting material when treated with the reagent like as a chloro P OET twice in presence of this one ETN, then isopropyl group, diisopropyl group. This is a tertiary amine used over there, and what it gives, instead of this one, what you are going to get here, the product is this one. Here oxygen atom, then P, you can write here OET, here also as a OET, and equatorial position there will be COOMe, that is a ester group, and now here the acetyl group which is lying at equatorial position. Now here make the correction, please see here NHAC, so that remains as it is NH, that is a protected amine group. Then this you can draw OAC in the above OAC group, and here door side OAC acetyl group OAC, and this is also one of the glycosyl phosphide, and this structure you can call it as a structure number 3. Near about is a 97%, very high yield product is produced this one. So this is also as a glycosyl phosphide, glycosyl phosphide, this one phosphide, and by using that phosphide we can get as a different type of the compound. And let me show some of the different compound over here. Here look at, these are the compound where we can get here P, then O, then this one, there is a aromatic compound over there, and this side here again OAC, here is a acetyl group OAC at equatorial, not equatorial, here at axial position OAC, and here again as a OAC. This is a structure number 4 which is prepared in a very high yield, that is also as a phosphide. Another example we can write over here. Suppose let us see here one of the compound we can draw here, oxygen atom, then there will be oxygen atom, then here we can show this type of the compound like this, here O, then P, then you can show over here O, this one, this type of the structure we can show over here. Here is a methyl group, here you can Me group, here also has a Me group, then OAC, then here oxygen, another group is joined over here, this one, this group we can show over here, again OAC acetyl group, and here is a, here we can show as a methyl group, So these are the different structure. This is a structure number 5, we can call it structure number 5, structure number 4 and structure number 5. These are the different 4 phosphate I have shown over here. Starting from this we can get as this one, and now this also nothing but as a phosphate. So this is a figure number 1 shown over here, and the corresponding pinnacle phosphate 5 was however stable enough to be isolated in 67% yield. This is a 67% yield we are getting over there, and several phosphorylation reagents are now available for the preparation of glycosyl phosphites and with desirable reactivity. Factors known to affect the anomeric ratio in the preparation of glycosyl phosphate include the anomeric composition of the starting hydroxyl compound. For example, a mixture of galactosyl phosphate with an alpha beta ratio of 90:10 was obtained from 2,3,4,6 tetraobenzyl galactopyranose with an alpha beta ratio of 90-10%. And solvent also affect the product composition. Phosphorylation of 2,3,4,6 tetra O acetyl galactose in DCM means dichloromethane gave the dibenzyl phosphate with an alpha beta ratio of 1:2, and this increased to 1:6 when THF tetrahydrofuran was used as a solvent. Effect of Lewis acid and mild base on the anomeric ratio of the phosphate have also been reported. And now next point we are going to learn about the glycosylation using glycosyl phosphate. The first catalyst used to activate the glycosyl phosphate was TMSO-TF, that is a trimethylsilyl triplet. The mechanism of the reaction has been investigated and shown in figure 2, and path A applies when TMSO-TF is mixed with donor first or added into the mixture of donor and the acceptor. And in this method the formation of substantial amount of phosphate orthoester is a considerable problem. As illustrated in path B, however, a premixed solution of TMSO-TF and acceptor spontaneously generate tryptic acid, that is a TFOH. TFOH thus activate the glycosyl phosphate added subsequently to give the desired product and reduces the formation of the orthoester. The most facile method is through path C, where TFOH directly catalyzes the glycosylation and also reduces the nucleophilicity of the hydrogen phosphonate. Let us see how the reactions are taking place over there, that I am trying to show over here. Let's see, this is the glycosylation, how TMS can be shown over here. Let's see here the first one, A path. I am representing some of the reaction TMSO-TF. TMSO-TF TF reacts with the donor first. Reacts with donor first. And what it gives, let us see here. I am representing this group at equatorial peak OET twice, and here must be OAC, acetyl group. So when it is not OET here, make the correction, benzyl group, then it will be treated with TMSO. What does it give? It gives this type of the structure over there, O, then O. Here is a positive charge, OTF minus this type of the salt is formed there, and when this salt further treated with TMSO, trimethyl silyl POBN twice, it produce this type of the compound O, here P double bond O, and in the bracket we can write OBN twice. This is a structure, and when it is treated with ROH and here also further treated with ROH in presence of TMSO, TF, both are producing the same structure OR, and here OEC. That is a glycoside. Starting from the phosphite, this is nothing but as a glycosyl phosphate, glycosyl phosphate, and from that we can get as a phosphate. From that we can get as a glycoside. From that we can get as a glycoside derivatives, and this further treated with, or here the generation of trifluoric acid HOTF, and that is further treated with TMSO OET twice, OBN twice, that produce trimethyl silyl triflate. This is a simple procedure where we can get this TMSO TF reacts with the donor first. So this is a glycosyl phosphate, and from that we convert into an intermediate that is further converted into as a glycoside. So in this way TMSO can act as an donor. Let us see another point over here, how it can be shown over here. Let's see the TMSO TF react with acceptor first. TMSO TF reacts with acceptor first. Reacts with acceptor first. Let's try to draw here. And as we know that HOR, when it is treated with, or it is further converted into HOTF, that is a trifluoric acid, and that trifluoric acid further here is TMSO TF, which is going to convert into here like this. There will be this one, we are getting OR and the OEC, glycoside formation once again form over here, and from this we can get this compound once again, O, this one positive charge OTF, that type of the not salt here. Let us see. After that we will get OAC, then O, P, O, BN twice. This type of the phosphate we are getting, and from this phosphate it may convert into HO, then POBN twice, and that will be converted into H, P double bond O, then OBN twice, and from this we can get an intermediate like this, O, positive charge OTF, and this intermediate is generally converted into as a this type of the glycosides. So this is a trimethylsilyl triplet reacts with acceptor first, and finally let us see, this is a B point, and now let us see the third point what we are going to discuss here. Let's see third point, that is a C point, that is when TFOH was used. When TFOH was used. When TFOH was used. So let's see over here, glycosyl phosphate, as we know that this is a glycosyl phosphate O, POET or BN twice, BN benzyl twice, that is a OAC. This is a phosphate taken, then that will be treated with HOTF, that is a trifolic acid. You may get over here this one O, this one positive charge OTF minus charge like this, and then it will be treated with alcohol. It gives this one as usual OR, and here is OAC. That is a glycoside once obtained over there, and from this also we can get OBN twice, and it is an glycosylation process. This is a glycosyl phosphate, and from that we are getting this one. So it may convert into as a P double bond O, then OBN twice. So these are the point you should remember as far as glycosidic phosphate is concerned. I think with this we have completed as a point of discussion of a glycosidic phosphate. In the next lecture we are going to learn about glycosylation method, use of N-pentyl glycosides. With this, let us stop today here. Have a nice day. Thank you.